Hello and welcome. Today we're diving into the fascinating world of calculus to explore some of its most fundamental concepts. Whether you're a student of mathematics or engineering, you've come to the right place. We'll be breaking down Rolle's theorem and the Lagrange's mean value theorem, also called as LMVT, step by step examples. So grab a notepad and let's get started. First up is Rolle's theorem. This theorem gives us a special condition under which a function must have a point where its rate of change or derivative is zero. The theorem states that for a function, let's call it f of x, defined on a closed interval from a to b, if three conditions are met. 1. The function must be continuous on the closed interval from a to b. Think of this as being able to draw the entire curve without lifting your pen. 2. The function must be differentiable on the open interval from a to b. This means the curve is smooth and has no sharp corners or breaks. And 3. The value of the function at the start, f of a, must be equal to the value at the end, f of b. If all these conditions are satisfied, then Rolle's theorem guarantees that there is at least one point C between a and b where the derivative is zero. Geometrically, this means there's a point where the tangent to the curve is perfectly horizontal. Let's verify this with an example. Consider the function f of x equals log of x squared plus 2 minus log of 3 on the interval from -1 to 1. First, is it continuous? Since x squared plus 2 is always positive, the logarithmic function is continuous everywhere on this interval. So, condition 1 is met. Second, is it differentiable? The derivative f dash of x is 2x divided by x squared plus 2. This derivative exists for all numbers in our interval, so condition 2 is met. Third, is f of -1 is equal to f of 1? Let's check. F of -1 is log of -1 bracket square plus 2 minus log of 3, which is 0. And f of 1 is log of 1 bracket square plus 2 minus log of 3, which is 0. They are equal. Condition 3 is met. Since all conditions are satisfied, we just need to find our c. We set the derivative equal to 0. 2c divided by c squared plus 2 equals 0. This is only true when the numerator is 0. So 2c equals 0, which means c equals 0. Since 0 is inside our interval from -1 to 1, Rolle's theorem is verified. Now, let's move on to a more general version of Rolle's theorem, known as Lagrange's mean value theorem, or LMVT. LMVT has similar starting conditions. For a function f of x on an interval from a to b, it must be continuous on the closed interval and differentiable on the open interval. We just don't need the condition that f of a equals f of b. The theorem states that if these conditions hold, there must be at least one point C between a and b, where the derivative f dash of c is equal to the average slope of the function over the entire interval. Let's verify this for the function f of x equals log of x on the interval from 1 to e. The log function is continuous and differentiable on this interval, so our conditions are met. According to LMVT, there must be a c such that f prime of c equals f of e minus f of 1 whole divided by e minus 1. The derivative of log of x is 1 over x, So f prime of c is 1 over c. We also know that log of e is 1 and log of 1 is 0. Substituting these values in, we get 1 over c equals 1 minus 0 divided by e minus 1. This simplifies to 1 over c equals 1 over Kesher e minus 1, which means c equals e minus 1. Since e is approximately 2.718, our value for c is about 1.718. This value is clearly between 1 and e. And just like that, the mean value theorem is verified. LMVT is also incredibly useful for proving inequalities. Let's look at another example. To solve this, we'll choose a function. Let f of x be tan inverse x on the interval from a to b. This function is continuous and differentiable everywhere. The derivative is f dash of x equals 1 over 1 plus x squared. By the mean value theorem, we know there's a point c between a and b such that the derivative at c, which is 1 over 1 plus c squared, is equal to tan inverse b minus tan inverse a all divided by b minus a. Now we use the fact that c is between a and b. Since a is less than c is less than b, it follows that a squared is less than c squared is less than b squared. Adding 1 to each part gives us 1 plus a squared less than 1 plus c squared less than 1 plus b squared. Important note. Remember that inequality signs flip in two common cases. When you take the reciprocal of positive terms and when you multiply or divide by a negative number, or as you might think of it, changing signs from positive to negative. So for our key step, we'll apply that first rule. We take the reciprocal of our inequality, which has all positive terms, and that means we must flip the signs. This gives us 1 over 1 plus b squared is less than 1 over 1 plus c squared, which is less than 1 over 1 plus a squared. We're almost there. Now we replace the middle term with our expression from the mean value theorem. Finally, we multiply the entire inequality by b minus a to get our desired result, and the inequality is proven. And there you have it, a complete walkthrough of Rolle's theorem and Lagrange's mean value theorem. Understanding these theorems is crucial, as they form the bedrock for more advanced topics. In calculus and engineering, such as Taylor series and harmonic analysis. We'll be covering our next topic, Taylor series, in the next video. So if you found this video helpful, please give it a thumbs up, share it with your friends, and don't forget to subscribe for more tutorials. Have a question? Drop it in the comments below. Thanks for watching and see you next time.